Hello, I hope that all of you are fine. Welcome to another lecture of robotics and automation. In the previous lecture, we studied about PLC and ladder logic programming. We also had a few examples of ladder logic programs. So in today's lecture, in the beginning we shall study about PLC timer and then counters, and then later we shall have some more examples of ladder logic programming for PLCs. Okay, so let's begin. The timer is used to indicate that the input is turned on, off, or to create a delay. So this is the use of the timer, and on the other hand, the counters are used to count the set of events that have occurred, and the latch or unlatch is used to lock something on or to turn it off. So for a PLC timer, if we talk about a PLC timer, the PLC timer consists of internal clock, a count value register, and an accumulator. And the timer is mostly used for timing process. So in a PLC timer, this is a timing diagram, and this is its symbol. So as you can see, this is a timer symbol, and it has a start input, then we have a delay input, delay time, and then we have input for reset, and finally we have output. So this is a basic symbol of a timer. And then the start input, previously it's off, and when it's on, okay, the output doesn't instantaneously goes on, but it goes on after some delay. Okay, as long as the input stays on, the output also stays on, and when the input goes off, the output also goes off. So this is a delay on timer. So the output will come at delay, with some delay, the time t. Okay, this is the delay time from here to here. So this time t we call delay time. Okay, so this is the on delay timer, and of course you can add delay in the later stage also, and that we shall study later. So many of the control tasks would need the programming of time, and so that's why we are studying timers, because we need time programming. Of course there are delays involved for, let's say, in a conveyor belt, when you're timing the sequence, so there are delays involved. So that's why we need timer. The timer instructions are used in PLC to create the program time delays. The number of timers that we can use in our program is dependent on amount of memory in the CPU. The timers are used in PLC to delay actions. The timer would keep an output for a specified time after an input turns off. So this is another type of timer, and that we shall study in the second section. The timer would also keep an output off for a specified time before it turns on. The major function of the timer is to keep an output on for a specified length of time. A timer has certain parts such as time base, accumulated value, timer address, preset value. There are bits that are related to current state of the timer, and it is called the status bits. The timing functions are inevitable in PLC applications. The cycle time is really critical in many processes. The timers in PLC are considered as software module, and it would generate digital timing. There is memory space in the PLC to store the delay time. Okay, now need for timer in a PLC. In many of the PLC control tasks, there is a need to control the time. An example of this will be using a PLC to control a motor. The motor would require to be controlled to operate for a certain interval, and that's why PLCs have timers. And the timers are built-in devices in a PLC. By using the internal CPU clock, the timer would count the time. Different PLC timers are programmed in different ways, so we can consider a timer to act as a relay with coils, which would open or close when it is energized according to the preset time. Timer instructions. The timer instructions are output instructions which is used to time the intervals for which the rung conditions are true or false. The timer accuracy will be dependent upon the microprocessor which is being used. The timer instructions is composed of two values, and they are accumulated value and preset value. So let's see what is accumulated value. This is the current number of time-based intervals that have been counted from the moment when the time is energized. So it's actually the time that has been passed since the timer is started. So this is called accumulated value. Okay, it's like a stopwatch. You turn it on, and after, let's say, 10 seconds, the accumulated value will be 10. Okay, and then you have the second one is the preset value. This value is set by the programmer. If the preset value is less than or equal to accumulated value, then the status bit is set, and this bit is to control an output device. So what happens is, let's say if you want to set your timer to 60 seconds. Okay, so if the preset value is less than or equal to the accumulated value, so what happens, let's say you set your preset value equal to 60 seconds. Okay, and your accumulated value, that is, let's say, 70 seconds. So in this case, the preset value is less than the accumulated value, and what will happen, the status bit will be set. Okay, its value will be set, and this bit can be used actually to control some output device. We shall see in the upcoming examples how we can do that. Each timer is composed of two status bits: timer enable bit and done bit. Timer enable bit will be set if the rung condition to the left of the timer instruction is true, and when this bit is set, then the accumulated value will be incremented on each time base interval till it reaches the preset value. So this timer enable bit, this is actually a status bit which shows that your timer is now enabled. Okay, so when the condition on the left side, this is true, then this enable bit will be, its value will be 1. Okay, and then the timer will start counting, incrementing the value. And the second bit we have is the done bit. this bit will be set if the preset value and the accumulated value are equal, and it will be reset if the rung condition is false. So once you turn off the condition on the left side of the timer, when it goes false or the switch is off, then done bit will be 0, and if the cumulative value of the timer it's actually it's equal to the preset value, then this done bit will be 1. There is actually one more kind of status bit in the timer, and this is called, we have timer timing bit, or TT bit. So this timer timing bit, its value is equal to 1 as long as the timer is timing. Okay, value is 1 when the accumulated value is less than the preset value. So, and otherwise it will be 0. So this is again a status bit, and these 3 bits, they can be used for as an input to turn on and off other outputs in your ladder logic. So now let's quickly see how the timer works. A timer will be activated if the execution condition is started, and it will be reset if the execution condition stops or goes off. So the execution condition, what this actually is, we have also encountered this thing, rung condition or execution condition. This is actually how to say, you remember we have in the ladder logic we have rung here. Okay, so in a ladder logic diagram, we have this ladder like structure, and then we have rungs here. Then again we have something like more structures. Let's say this is motor, this is S1, S1, S2. So this is the first step. We call it rung. This will be rung 1, rung 0, sorry, and then second will be rung 1, and so on. We have rung n, depending upon how many steps you have further in the ladder diagram. Okay, and these are on this side. You notice that here these are the actually the rung conditions here. Rung condition, you can call them, or you can call them execution condition. So when you have, this is the execution condition. Okay, let me write down here. I'll just call it okay. So this is now clear. So what it says here is that the timer will be activated if the execution condition is started, and it will be reset if the execution condition stops or goes off. So as long as let's assume that here you have a timer, okay, and as long as this switch will be on, okay, or the condition is started, the timer will be activated, okay, and it will be reset. It will become again the reset condition as you turn off this switch, okay. So if the execution condition keeps ongoing, or if it's long enough for the timer to time down to 0, then the completion flag will be turned on, and it will remain on till the execution condition is completed or turned off. So what's happening here is that your timer has also a completion flag, or you can also call it a timer timing status bit, okay. And so as long as your timer is running, this bit will be remain 1, and when the timer is completed, its accumulation is completed, okay, and then this status bit, timer timing bit, it will become again 0, or it will be off. The address of the timer is unique in the PLC memory. The timer instruction is one element, and the timer element is composed of 16 bits. So it's a 16-bit, you have there 16 bits, and there are actually two words, word 0 and word 1. The word 0 will cover the status bits, and it has 3 state bits such as EN, TT and DN. So we have already, this is the timer enable bit, this is the timer timing bit, and this is timer done bit. As we have studied here, this is actually EN. If I like to call it, this is EN, and this is the done, timer done, and this is the TT. Okay, and here we made a mistake, in a spelling mistake, logic diagram. Okay, so we have here 3 status bits in the word 0, which is the enable bit, timer timing bit and timer done bit. The word 1 is for the preset value, and the word 2 is for the accumulated value. So we have here also a preset value. Preset value is the value that you want the for the maximum time you want to be delayed, okay. And then there is a word in which you have the accumulated value, like the actual real time, actually the time that is being passed right now. Let's see examples. First we see a general example in which we have a timer, and then we see these values. Okay, normally here we have a timer. This is the diagram for the timer, and this is how it looks like, a general timer here. And this is, you have here the timer enable bit, EN, okay, and then you have here timer done bit, which is DN, and then you have the, let's say, the name of the timer, and this is, we call it T on timer, and then you have the address or the step size of the timer, and you can also, yeah, so we call it time base. So time base is actually the step size actually. So let's say this is 1 second, and then you have preset value. Preset value is the maximum value that you want to count to. This is, let's say, 60, and then you have accumulated value, and this is actually the starting from 0, it goes incrementing by each step. Okay, and then you have an input to the condition to the timer, and so this is the basic of the timer. So how it works is it starts from the 0, and the step size that you have defined here is actually add you see 1, it increments 1, and then till it reaches to 60 value, and then your dn bit will be its value will be 1. So for further detail, we shall also see there are two types of timers. The first one is the on delay timer, or we call it T on, and the second one we have the off delay timer, we call it T off, timer off. Okay, so let's see what is the on delay timer here. So on delay timer, it actually works like this. When you have your input, when your input is goes up, okay, when input is on, the output will be on after actually some delay. So that's why it's called on delay timer. So it works like, let's say this is the input we have, and the input goes up like this and goes down, and then you have output here, and the output will not instantaneously go up, but after some delay it will go up and it will go down. So this delay that we have here equal to delay time t, equal to the preset value that you have assigned here. Okay, so in this case you have here, let's say 120, the preset value. So after t is equal to 120 seconds, your output will be value will be equal to 1. So this is, let's say, 0, and this is 1, this is 0, this is 1 here. So that's how it works. So let's see in detail. This type of timer can be seen in small PLCs, and this timer would be on after a particular time delay. Would be on after a particular time delay. This is widely used for PLC programming. We can also create other timer functions by using an on delay timer. So this timer would delay the turning on time in a system. This type of timer would count the time base interval if the instruction is true. So if the run condition becomes true, then the on delay timer instructions will start to count the time base intervals. So if the run conditions stay true, then the timer would adjust its accumulated value during each evaluation till it reaches the preset value. So when the run conditions becomes false, then accumulated value is reset. The three timer bits EN, TT, and DN can be used as run conditions. So let's again have a look on this diagram. We have this T on timer, on delay timer. Here you have the input where you have some run conditions. When this is true, okay, when this is 1, when the run condition is, input condition is 1, timer is the timer enable bit will be 1, okay, but the timer here you have also one more output, which is the timer. So as your input is 1, it means your timer is enabled. This status, timer enable status, will be 1, but your timer and your timer done both are 0 now. For now, okay, they are 0, and your accumulated value, this is equal to 0, and your preset value is 120. So, and your time base, the step size is 0.01. okay, this is the step size. So starting from 0, the timer will start counting as soon as the condition becomes 1 and timer is enabled, and both of these are 0. And once your accumulated value reaches equal to your preset value, okay, then what will happen, your done, there is a mistake. So your timing value, this will be 1 initially, because timer now is timing. This is accumulated value is increasing, timer is now working, okay, it's processing the input clock. So now initially it's 1, but the timer done bit is 0. As soon as your accumulated value will become equal to your preset value, okay, so what will happen here, in this case, your timer enable will remain 1, okay. So I'm talking about when the accumulated value become equal to your preset value. So what will happen, initially your timer bit will goes from 1 to 0, okay. Your timer done bit will goes from 0 to 1, but your timer enable bit will be in this case remain same. But as soon as your input goes from 0 to 1 to 0, then what will happen, your timer enable bit goes from 1 to 0, and your timer done bit will goes from 1 to 0 again, and this is already 0. So this is how it works, and I think this is a little bit confusing. So let me just okay, I think now it looks better. Yeah, so this is how the T-on timer works, okay, and let's see how we can use it in the ladder diagram. So here we have a timer, and this timer is the type is the T-on timer, which is the delay on timer, and the name of the timer is the, here we have the name of the timer. If you want to address, this is T40, and the base value is 1, preset value is 180, and it will start from 0, okay. And here you have the timer enable bit, timer done bit. Usually the timer timing bit, the TT bit, it's not usually shown here. Actually, they don't show it. I'm not sure why they just skip it. And here on the left side you have input and or the condition, you can say the rung condition. This is rung 0, rung 1, rung 2, and here you have a switch here. The switch is input I 0, 1, 2. When the input condition is true, the processor increments the accumulated value of T40, this is the name of the timer, in 1 second increment. So as long as this condition is true, or this is equal to 1. So the timer will start incrementing. Okay, this accumulated value, this will be 0, and then 1, then 2, and continuously adding 1 till it reaches 180. Okay, so the accumulated value is equal to this will be equal to, we have here, plus preset value. So this is your final. So if your accumulated value is initially 0 and preset, not preset, it's a time base, sorry, plus time base. So 0 plus 1 is equal to 1, and then 1 plus 1, 2, 2 plus 1, 3, 4, 5. So this is how. And once your so right now this enable is 1, okay, because the input is 1, the condition here is true, and the timer is enabled, it means, and this TT bit is also 1, okay, but this DN bit, this is equal to 0 because timer is not done yet, it's still timing. Okay, and this is how you can use these status bits for other. So we made another rung in the ladder logic diagram where you have the timer timing status as an input, okay, and then you have here an output. Let's say here we have a motor M1, okay. So as long as the timer is timing, okay, this bit will be 1. This is 1, and once it's 1, this is true, then what happens? Your motor will be running, okay. And the DN bit, because the DN bit is 0 now, for 0, so what will happen here is that the this will be 0, this is false, is equal to 0, and the switch is open, so this motor M2, this will be stopped. So this is these are the outputs when the timer is still not done yet. Okay, and let's add one more condition here in the ladder diagram. Let's add one more rung, and in this rung we have one more input and output conditions. So this is the EN status bit here, okay, and this is motor 3. Since the EN is 1, timer, because the EN depends upon actually the input. If input is 1, the TN is 1. This is for T on timer, and this is true. So this will be, your motor 3 will be on also. Now let's see what happens when the timer is done and your accumulated value if accumulated value is equal to the preset value. So now what will happen? If accumulated value is equal to preset value, so now in this case what will happen? This your timing bit, it will goes to 0, as we have studied here. When your timer is done timing, this TT goes from 1 to 0. It goes 1 to 0, and your done bit, it goes from 0 to 1. So this is the only changes we have. Okay, this will remain on as long as your input is on. So what will happen now? Once the timer is done, here you have also value is equal to 180. means here 180. So in this case, these things will happen, and now your timer timing bit is, this goes to 0, okay, and this also becomes 0 because now the switch is open, motor will stop. The timer done bit, previously it was false, the motor was off, but now it will become 1, okay, and the motor will become on. For the timer enable bit, it will remain the same. Previously it was 1, it will remain 1, and the motor is again on. So this is the advantage of T on, or the delay on timer we have. And yeah, now let's see the delay off timer. So delay off timer, this is actually almost opposite of the T on timer. So what happens that once you turn off the input, okay, so your input, this is, let's say, your input, previously it was on, and once you turn it off, okay, so what will happen, let's make this a little bit, so this is 1 here, and this is 0 state, and for the output we have, it will look like this. Zero, and this is the delay here. This is the delay off timer. So when the input goes off, the output will not go off instantaneously. It will take some time and then it will become off. Okay. So the delay off timer, or you can also call it TOF, this is the figure of this timer. It has almost similar kind of, it looks similar, only the name is different. You have the name of the timer, and then you have you have to define the step size or the base, and then a preset value, and then there is also the values that will be accumulated with the passage of time, and then you have the enable bit and the done bit, and also there is also one bit, it's called timer timing bit. And so let's see, this is the exact opposite of the on delay timer. This timer would delays the turning off, so these timers are on for a fixed period of time before turning off. So that we have mentioned here, that before going off they will stay on even if the input goes off. The output will be turned off after a delay. So when this timer is turned on, then the output is also turned on. And the other thing is, once you again you turn on the input, and the output will also turn on very quickly. So what we are referring here, the output is actually the DN value here. So this is, we are referring to the output. Okay. So if the output needs to be turned off, then it needs to be turned on in the beginning. So this timer won't be activated before we turn the input off again. So if we do that, the timer will start the count after the delay and the output will be turned off. So let's try to understand this with the ladder logic diagram we have here. This is the delay of timer and its preset value is 180 seconds because the step size is 1 second. And so let's imagine with the red dot we say that the timer is already on, okay, because the input is on. And then in this case your enable bit will be on, and your done bit, this will also be on. And there is also one more bit, it's timer timing bit, and this bit will be off. So right now this both of the enable and done bit, they are on, and timer timing bit is off. So here we have used the status bits of the timer as inputs, and let's add one more rung in this ladder, and this rung will be let's say this is the enable bit here, en. So the output we have here, we have motor 1, we have motor 2 and motor 3. And so once the input is 1 on, so enable bit and the done bit is 1, both they are 1, and you have the timer timing bit is equal to 0. So they are used here as an input again. So here we have timer timing bit, done bit and enable bit. So right now this is 1, enable bit is 1, done bit is 0, done bit is also 1, and timer timing bit is 0. Okay, so it means right now the motor, this motor will be off, this will be on, and this will be off. Okay, so this will be 0, this will be 1, and this will be 1. Now what happens when we turn this off? So this goes to 0. So once your input goes to 0, what happens that in this case your timer enable bit, this will goes to 0, okay, and timer timing bit, it will goes to 1, and now the timer will start here. Okay, the timer will start here and it will start accumulating value till it reaches 180. Okay, and meanwhile it's accumulating value, and the value is less than 180. So what will happen, we have the done value in this case will be unchanged. Okay, only the enable and TT value they're changed. So in this case we have the this TT will be 1, and this DN remains same, and enable goes to 0. Okay, and once your accumulated value is equal to the preset value, so once accumulated value is equal to the preset value, So in this case, what will happen, this is already, so in this case your this done value, this goes to 0. So in this case others, where is the done, so in this case this goes to 0. Okay, okay, so here we just arrange it a little bit more, so we missed that this green step when this one here, because when we switch from 1 to, when our input was 1 to 0, so the D and the done bit was unchanged. Okay, so this was unchanged, but in the next step, when the accumulated value become equal to preset value, then this became, done became 0, and also this became 0, and this was already 0. So these, both of the timer timing and the timer done bit, they both became 0, and this was initially, it was already 0. So yeah, this is how the delay of timer, this is how it works. And yeah, okay, one more thing I like to point out here is that if you want to reuse this counter, sorry, this timer for one more time, okay, for example, if the previous cycle is completed, the previous time is completed, and your timer is now finished timing. Okay, now your accumulated value is equal to preset value, and the delay is finished. So we have reached this state. So we have reached this state here. So to again use this timer, what you just need to do is to turn off the timer and then turn on it again. So basically you have to make this condition, the input condition, is equal to false for the delay on timer. So once you make it false and then you again make it true, so it will start behaving again from here, false and then true. It will again give you some delay with the output. Okay, and same is true for the, not same is true, but it's similar for the off delay timer. So in this case you have to turn on the input again, and once you turn on the input again, the output will also be 1, and output will be 1, and again when you turn on the input, there will be some delay in the output. So yeah, so these are timers that we use in PLC, and then we have the counters. Now let's see what are the counters and how we can use them in the PLCs. So this is the detail of this thing, the counters, how they work. But what we are going to do, I'm just basically explain the up counter and the down counter and how they actually operate. So counters, they are used actually for counting the number of events in the input side. Okay, so they're useful, for example, if you have let's say if you have some objects on the conveyor belt, and for example, if you have some objects, you have a conveyor belt, and there are some objects on this conveyor belt. And then here you have a sensor that senses these objects, and it's also connected to PLC. So what you need actually is this sensor is actually connected to a PLC, and in PLC there is a counter that counts the number of pulses that are being created by this sensor. So what you need is you actually need a counter. It can be an up counter or down counter. So up counter is actually, it has number of inputs. C up, this is an input that is connected to here, C up, and then there is an input for reset, and there is the value the maximum value, the maximum upper limit for this counter. This is also the preset value, and then you have a count value, how many objects have been counted, and then you have the counter done, a counter status bit. So what happens is that as these objects will pass, so there will be a pulse generated by this sensor, and for each pulse this counter will add 1 to the counter. Okay, so, and this value will be output, this value will be shown in this output, that is CV, and once this is a limit, PV is the limit, upper limit, and once your number of objects, okay, number of counts are equal to or greater than this upper limit, then this status bit of the counter, it will be 1. Okay, as long as the number of counts are less than your upper limit of the counter, this will be 0. As soon as the counted objects are equal to or greater than your upper limit of the counter, then the Q will become 1. Okay, and CV shows the number of counts, how many objects have been counted. When you actually use some programming language, ladder logic, so this is a count up timer, and this is type, and the name of the counter is C30, and the preset value is 10, which shows that the 10 means it wants to count 10 objects, and till now it has counted 0 objects. And here you have the input here, and this is the output here, and for every step it will add 1 to the accumulated value until once it reaches 10, then the output will be the status of the output will be 1. Okay, so here the value will be here done, it will become 1, and so previously it was 0, and then it will become 1, and here the counted values will be shown here. And similarly we have also a down counter, and the down counter is actually opposite to the up counter. and for the down counter we have the actually some preset value, and for every input so what happens, there will be the value is subtracted from this preset value, okay, and once the this value becomes 0, then your status of this counter will be the output will be 0 to 1, okay. And there is also one more counter, it's up down counter, but we are not, we just ignore this one. So yeah, so we have now up and down counters, and what we need to do is now to use them in the ladder logic, so we can actually program something with timers and counters. And let's also have some more examples of the ladder logic, and there we can actually practically use these timers and counters. Okay, so let us see some more problems about the ladder logic programming. And so we begin our first problem here, and here it says that design a ladder logic diagram that provide lubricant for the gearbox before the lathe spindle starts to run, which aims to ensure that the oil pump motor starts first and the main motor starts subsequently. So this is for lathe machine. You have to design a ladder logic diagram, and then you have some buttons, push buttons. S0 is start push button to start oil pump motor, and then you have the S1 button, and it is start push button for to start main motor. And then you have S2 button, which is stop push button to stop oil pump motor, and then S3 button, which is stop push button to stop main motor. So there is one oil motor, oil pump motor, and then there is main motor. So there are two motors, and you have to start them and then stop them. So let's see what is the ladder logic diagram. Is given below. So this is the ladder logic diagram for this problem. So first you have a switch, and this is actually a push button, not a switch, it's a push button, and this is normally open. Okay, normally open means normally it will be, the current cannot pass through here, and so this is NO means normally open, and NC means normally closed. Okay, so these are the differences. So when the switch, not the switch, this is actually push button. So when the push button 0 you press the push button 0 and the stop button for the which is S2, which is the stop button for oil pump motor. So when you press S0, what will happen? The oil pump motor will start moving. So M0 is the oil pump motor. So it will start as long as the stop push button is not pushed. Okay. And once the oil pump motor started, so there is again here you can see the latching. This is called latching. So there's a latching where the status of the motor is used as an input, as a condition for the whole rung, and this we call it rung 0. This one, rung 0 we have here. And so once the motor is on, this switch will be on, and then you don't need to actually press the button, push button for a long time. You just need to press it once, and then the latching will start, and the alternate path of the current will be here. Okay, so this is for the oil motor here. So this was the oil motor. So now the oil motor is running. Okay, and so the second is start push button to start main motor. So now you have to press a button to start the main motor, but the condition is the oil motor is already running. So you can, this is for safety. This is for safety that the lathe machine lubricated already. Lubrication is already being performed before you turn on the main motor. Okay, which is M1. So for that you need a push button. When you push this S1 button, so it means the stop button should be unpressed, and the motor the oil motor, it means it's already running. So once it's running, switch will be closed, this will be closed, and your main motor will start running. And once it start running, there is again a latching action here where the output of the main motor is being used as an input, and then because you don't need to press the push button for a long time, just press it once, and then your main motor will start and it will keep running. And if you want to turn off, okay, so you have to press these push buttons S3 and S2, then your both motors will stop. So this is the solution for this problem. And yeah, so here this was rung 0, and then the second one is rung 1. So in 2 rungs you have solved this programming problem. Okay, now let's move to our next problem, which is problem 2. So in this problem, it says that design a ladder logic diagram for a staircase lamp that can be turned on off by 2 switches located at the top and bottom of the stairs. Human should be able to on off the bulb using any of the 2 switches. So here, this is the diagram of this problem. So you have stairs, like you can see there's a door, and there is a switch, and then you can a person can climb the stairs, and then there is a door for the first floor, and there is a lamp. So what happens in the night, there is one lamp, and so instead of using two bulbs, one here and one there, so what the problem is that you have to control this lamp from either of these two switches. For example, if a person is standing here, so he must be able to turn on the switch, turn on the lamp using this switch 2, and when the person is standing here at this location, and so it can be also able to turn on and off the lamp. So you have to design a ladder logic diagram circuit using this PLC. So this is the solution. So what you have to do, you have to, because there are two switches, switch 1 and switch 2, so that switch can be on and off. Okay, so in this case, what is the thing is, this is the normally open, the switch 1, the first condition is that in the rung 1, so rung 0, there is a normally open switch 1 and a normally closed switch 2. So what will happen here, when the switch 1 is normally open and switch 2 is normally closed, so the lamp cannot be on, it's off. Okay, because there is no way the current can pass. Now what happens when you press this switch 1, for example, the user is here and switch 1 is normally open and switch 2 is normally closed, and once you press this switch 1, so this circuit is closed, this switch is closed, and the current will start passing and the lamp will be on. Okay, so now the circuit is closed and the lamp is on. Okay, what happens if now the switch is, this switch is closed, switch 1 is closed, and now the person, let's say, climbs down and it comes here. Okay, and what will happen here is that one thing is that when the person was here, so what we are here assuming that when he pressed this button, switch 1, he is assuming that switch 2 is already in a closed state. Okay, but this is not a must. Okay, it's also possible that the switch 2 was in an open state. Okay, so in this case you need two OR conditions. So there is AND between switch 1 and switch 2. Okay, and also there is an OR between these two things. So that's why we have to include one more line where the configuration is inverted. Okay, here we assume that the switch 1 was open and switch 2 was closed, but the other possibility could be that switch 1 is closed already and switch 2 is open. So these two are the possibilities. So for the first case, if this is a case, if switch 1 is open and switch 2 is closed, then you just need from the top floor, you need to switch on the switch 1. Okay, turn on the switch 1 and then your lamp will will turn on. And if you want to turn it off just from the top floor, turn off this switch 1. So it means when you are on the top floor, you have only control on the switch 1. Okay, and once a person is on the ground floor, then this condition will apply here. And so in this case, it's not must this condition, but it's a alternative condition, you can say. This is another possibility. Let's say if the switch 2 is open, then he has to turn on the switch, so that if in case the switch on the top floor is closed, then your lamp will start glowing. If this is not the condition, if the condition is that in the ground floor the switch 2 is already closed, the switch is closed, then it means that and still the bulb is not on. Okay, so if the switch is closed, switch 2 is closed, and yeah, so if the switch 2 is closed and the switch 1 is open, okay, then the from this condition the bulb will not on. But if you close the switch and the switch 1 also closed, and this is another condition, then your bulb will start glowing. And if you want to turn off this bulb, you have to just turn off this switch 2, and that's how you control the control your bulb from either your ground floor or your top floor, where your switch 1 is located. So after that, there is in the rung rung 0, and then in the last rung you have to finish your program, ladder logic program, with an end. And just keep in mind that this was for the this condition was for the top floor, and while this condition, this switch was for the ground floor. And top floor. So these are the two you can say two switches that can be controlled from two different floors we have. I think this just makes the things complex. So okay, so this was the solution to our problem 2, and now we move to our problem 3. So problem 3 states that the task is to control a simple machine which counts and batches components moving along the conveyor belt. It is required that 10 components to be channeled down route A and 20 components down route B. A reset facility is also required. So the problem is that, as you can see in this figure, you have a conveyor belt. So it's working in this direction. So objects are moving in this direction, okay? Direction of motion is in this direction. And so these are the components, or you can call them objects, and objects are coming from this side, and then there is a this is the conveyor belt that is split into two conveyor belts, okay? And the purpose of this is sorting of these objects. And then there is a touch switch that senses the presence or proximity of these objects and counts them, okay? So this is a flapper. This flapper is connected with a solenoid that can move in this direction, that can rotate in this direction. And so the purpose is to sort the objects, some on the left side, some on the right side. And so our desire is that 10 should be collected on one side and 20 on the other side, using this flap solenoid and this touch sensor. So you have to design a circuit for that, PLC circuit. So first let's see that how we can do in physically how can we do that. So this is our PLC here, and this PLC it has some inputs and outputs. So in this side, on the top side we have inputs, and on the down side we have outputs here. And so the output side is, you have 24 volts and then a solenoid coil. It's like a magnet that will move your flapper, okay? And the inputs to the PLC are, there's a start button that will start this whole process of sorting, and then you have a reset button that will reset these whole operation, and then you have a sensor input touch switch. This is to the input 2 of the PLC, and reset is input 1, okay? So this is your PLC here. So PLC programmable logic controller. Okay, this is the physical setup for this problem, okay? Now you have to design a software, the program for that, ladder logic program. And this is the ladder logic program. So input 2, which is the sensor input from the sensor, it is connected to a counter, which is counter 1, and the preset value of this counter is 10, okay? And this is the output of the counter, which is C1, and this counter can be reset by either the reset button, which is located at the input 1 of the PLC, or it can also be reset when your counter 2, which is located here, when the counter 2, the output of the counter 2 is set. So once either you press the reset button or counter 2 is set, then counter 1 will also be reset, sorry. So what happens here, the objects are coming on the conveyor belt and the touch sensor is sensing, and each time it gives an input, your counter will count 1. Then next object will come, it will count 2, 3, 4, 5, 6, 7, 8, 9, and once the objects are 10, then the output of your counter will be 1. Okay, it will be like set. Once it is set, so we shall use this in the rung. This was our in the next step here in the rung 1. What we do, we use the output of counter 1 as a input condition, and then turn on our solenoid flapper. So once your counter is done counting the 10 objects, it will move the solenoid in this direction. Previously it was here, and then once the 10 objects have been passed in this way, then the counter will set, and counter 1 will set, and it will move the flapper in this direction. And then what will happen? Then again your sensor, which is located at input 2 of the PLC, the sensor will start counting the objects, and as long as your counter 1 is set, okay, your counter 2 will start counting the input objects, and for counter 2 the preset value is 20. Okay, so it can count 20 objects, and once the objects are 20, the output will be set, and so it start counting, and once the output is set, C2 will be equal to 1. Okay, and once the C2 is 1, what will happen? This counter 2 is reset, and the counter 1 will also be reset, and your program will end here. Okay, the ladder logic program. So this is how you sort out the objects into batches and using PLC automatically. So here, yeah, so this was route A and this was route B, if I'm not wrong. Yeah, so this was quite easy, and this is also a practical example where you can use counters. And yeah, so let's move to our problem number 4. So problem number 4 says that design a ladder logic diagram for a fluid mixer tank. The fluid is pumped into the tank by 2 hydraulic pumps driven by motors M1 and M2. There is a mixer that is driven by motor M4, which operates for 500 seconds. After mixing the fluid, it is pumped. It is pumped out from the tank with pump 3 and motor 3. So with each pump you have actually motor attached. Pump 1 and pump 2 are turned on for 30 seconds and pump 3 is turned on for 60 seconds. The process begins when start button is pressed and can be stopped with a button. The whole process is cyclic. So this is not a push button, this is actually you can say it a switch. You can call it a switch also. Okay, motor 4 is, so here's the diagram. So what happens is that pump 1 and pump 2, they are the input pumps. They fill this tank with the with your fluid, okay, of two different kind of fluid coming from pump 1 and pump 2, and there's a motors M1 and M2 here. And then you have the mixer. This is the motor M4, and the mixer rotates and it mixes the fluid, two fluids, and then your pump 3 will turn on. So there is also timing involved. Pump 1 and pump 2 run for 30 seconds, and then your mixer motor M4 run for 500 seconds, and then after that your pump 3 will empty this tank by pumping out all the water, all the fluid, and this will run for 60 seconds. So what we have to do, we have to design a ladder logic diagram for this problem. So here, and that's how we start. So we have a start switch, and so this is not a push button, this is actually a start button where you can start the process, and then you have a stop button where you can stop the whole process, okay, and this is normally closed, and your start button is normally open. And once you press the start button, this circuit is complete, okay, and we are using here the T on type timer, and the timer name is T40. The step size is 1. The preset value is 30 seconds because this is for pump 1 and pump 2, okay. So it's given that it should run for 30 seconds to fill the tank, both of these pumps. And this is the accumulated value, which is initially 0, and with each step it will add 1 till it reaches 30, okay. And then we have the timer status bits EN and DN, and so in this case what will happen, this is a delay on timer. So once you press the button, the output at the DN will come after 30 seconds. So the DN is initially 0 and it will become 1 or true after 30 seconds. So note that here we are also using the input from another timer, output from another timer as an input. This I will explain it later when we are on timer, this T42 timer, okay. So what will happen? So we have pressed the start button, and now the timer is counting, still counting. It doesn't reach at 30. Let's say it's counting at 5 seconds, and your DN is still 0. Now what we are doing is that we are using the output of this timer T40. We're using the status bit, which is DN, as a normally closed button, and this is connected to motor 1, which is the pump 1. And the reason is that as long as your status bit DN of the timer T40 timer is as long as it's 0, so your motor is running, so it means your pump is pumping, okay. But once the 30-second time is finished, your DN will become 1, and this input will be changed. It will become open circuit, and then your pump will be closed. And since there are two pumps that should run in simultaneously, so we are using this same input for the second pump also. You may also connect this here like this also, to instead of using two separate inputs, you can use single input for two outputs also. So what happens that as long as your counter is not done, timer T4 0 is not done, your pump 1 and pump 2 are still running. Okay, after 30 seconds this will be done, it will be true, and both of these switches, they will be open, and your both pumps after 30 seconds will be closed. So now your pumps have pumped water into the tank for 30 seconds. So once your timer is done, okay, so now we can use the output of this timer to start the next timing process, now we have to mix this two fluids for 500 seconds. This is our next step. So now we are using the input from the previous output of the previous timer, which was T40, and once we say it is done, okay, so now it can start our next timer, which is T41. For this we have the preset value of 500 seconds and the step size is 1. So now once your T40 timer is done and your both pumps are stopped, now what will happen, your motor 4, which is a mixer motor, it will start because this is connected to the output of timer T41, which is a second timer, and because the timer is still running, it doesn't reach to the preset value, so the DN bit is still 0. As long as it's 0, this will remain normally closed, and when it's normally closed, the current will pass and it will turn on the mixer motor, and this will run for 500 seconds, and after that the timer will be done. This bit becomes 1, and once this bit will become 1, this switch will be open and then your mixer motor will be stopped. So once your fluids are mixed, then we can use the output of the timer T41 to turn on the next process, which is to pump out the fluid. So once your T41 timer is done, this switch will be closed and your timer T42 will start working. Okay, so this timer has a step size 1 and a preset value of 60 seconds, and because we have to pump out the water for 60 seconds, and so what we can do, we have used the output of this timer DN status bit as an input to our pump 3, okay, which is attached with motor 3. So as long as your timer is not done, this motor is moving because this is the normally closed. This is normally closed switch, and as long as the DN status bit is 0, it will be the pump 3 will be pumping out the fluid, and after 60 seconds this DN bit will be 1, and your this switch will open and your fluid, your pump will stop. Okay, once after that there is just, you have to end the program, and to make this program cyclic, what we need to do, we need to add the output of this, your final third timer, which is T42, with the beginning of timer, the first timer. because once previously it was open. Okay, so it has no influence to start the whole process again unless you press the start button. But because you want to make this thing cyclic, okay, so what you do, you add the output of timer T4 as an input, and once that the whole process completes, it means T4 is done. Now it can repeat. So once it's done, this button will be closed, and regardless of what, if you press the start button or not, let's say if it's a push button, so but I think this cannot be a push button. This cannot be a push button because if this is a push button, then your timer cannot actually cannot be enabled. So it must be a switch to continuously turn it on. So it means that this is actually not really correct. So let me correct this thing, and I think we can just remove this condition from here. Because this cannot be a push button. This can only be a switch that can be permanently. You press it, then it's on. So yeah, so start button, and then so for cyclic, because this PLC whole thing, the whole ladder logic program, it's cyclic. It starts from rung 0, and then and then you have the rung 1, rung 2, rung 3, rung 4, rung 5, rung 6, rung 7. So once it reaches at rung 7, it goes again back here, okay, and the process will be repeated again. So you need to actually add a timer here, not a timer but a switch here, that T4 2, and this is done, and this switch should be normally closed. So what will happen once your timer T4 is done, okay, and it means that your pump 3 will be stopped, and then what will happen, now you have to reset all your timers, okay, because they are already in the done condition. So once you this will be, you can do it either you can stop the whole process by pressing this button, stop button. When you press this stop button, this condition for the timer to enable this will be false, and what will happen, this goes to the enable bit will go to 0, and your done bit will also goes to 0, and once the done bit goes to 0, your this motor M1, because this switch will be open, this will stop, this motor 2 will be stopped, and then because this was 0, so the timer, the condition for the timer T for 1, this will also become false, and this timer will not also be enabled anymore, and this done bit will become 0, and in the consequence motor 4 will stop, and timer T for 2, this will also will not be enabled anymore, because the done bit from the previous timer is now 0, and the timer is disabled again, and the done bit will be 0. So this whole process will be resetted just by either by pressing the stop button, or by when your whole process is completed and timer 4.2 is done. So once it's done, this button will be open, and your timer T40 is disabled, your timer T41 is disabled, and your timer T42 is disabled, and it's done bit will be 0. And again, when the done bit is 0, then what will happen, this is again a normally closed situation, and your process will start again and from the beginning. So this is example of the ladder logic program. And yeah, so if you have any questions, you want to discuss anything, just contact me by email. And thank you for listening the lecture. So yeah, goodbye.